We're going to shift gears a little bit. So far, we've been talking about the level of employment of one variable input that maximizes profit for the firm. Now we're going to talk about what combination of two inputs minimizes total cost when we have a desired level of output we want to produce. The first question is, can firms ever reduce the total cost of production without reducing output by employing more of one input and less of another? The answer is yes. A firm can reduce total cost by employing more of one input and less of another in some circumstances. Here's an example. Suppose we have two inputs, K and L. Let's suppose that the wage for L is $5 and the wage for K is $15. Each L produces 100 more units of output and each K produces 200 more units of output. To make the analysis simple, we'll assume that these extra outputs, the 100 and 200, are constant over the relevant range. In a more realistic example, the extra output of L might decrease if we hire more L, and the extra output of K might decrease if we hire more K. We'll push that to the side to make the math so simple. Right now, we've got 8K and 10L. We're producing 1,000 units of output. We can calculate total cost pretty easily. Total cost of what you pay for is the $15 you pay for K times the amount of K you employ, plus the $5 you pay for L times the amount of L you employ. So 15 times 8 is going to give me 120. 5 times 10 is going to give me 50. So the total cost currently is $178. We can't do any extras, and we can't find marginal cost yet. Marginal cost, or MC, is the change in total cost over change in Q. Since we haven't changed Q yet, we cannot find a marginal cost. Let's look at row 2. In row 2, I've increased L by 2 units. Since each extra L cost me $5, my cost has risen by 10. Now what's going to happen to output if I increase L by 2? I know that output rises by 100 when L goes up by 1, so simple multiplication tells me that output will rise by 200 when I increase L by 2. Again, remember I'm assuming the extra product is constant over the relevant range. That tells me that my output's going to rise from 1,000 up to 1,200. My total cost is going to rise by $10. The new total cost will be $180. And I can very quickly or easily determine marginal cost. Output, total cost rose by 10. Output rose by 200. 10 divided by 200 tells me the marginal cost is going to be 0.05 or 1 nickel. Let's go from row 2 to row 3. In this pair of rows, I'm decreasing K by 1. I'm going to decrease K by 1, and now I'm going to save $15 in my cost. So my new cost is going to be $165. Since each K produces 200 units of output, or an additional 200 units of output, when I fire a K, I'm going to lose 200 units of output. Again, I'm assuming that 200 is constant over the relevant range, which means my new output is 1,000. The marginal cost will be 15, or negative 15, divided by minus 200, which is equal to 0.075. Let's compare rows 1 and 3. I'll do it in purple. Rows 1 and 3, output remains constant. I started at 1,000, I wound up at 1,000. But notice, my total cost went from 170 down to 165. I was able to reduce total cost while keeping output at 1,000 by hiring more L and less K.